In the past labs, we used QSAR biodegradation dataset to learn the performance of tree-based models and ensemble methods. Bagging, random forest, and gradient boosting machine um, learning. We randomly divided the dataset into two halves, the train set and the test set. We performed classification of tree tasks using model selection criterion of growing the tree and then pruning the tree by selecting parameter values to fit simple tree. Firstly, we pruned the tree by using the deviance method on tenfold cross-validation to get the best cost complexity. Secondly, the pruning was done using the misclassification method on tenfold cross-validation to get the best size. In both cases, the misclassification test error rates were more than that of the unpruned tree. Pruning by selecting best cost complexity parameter value gave higher misclassification test error rate, but the model is simpler compared to selecting by size. We perform tasks on ensemble methods of the bagging, random forest, and gradient boosting machine methods. The test set errors for bagging and random forest methods were very close. Bagging and random forest methods are the random forest models, but in bagging we use the list of all the predictors, but and in the other model we use the square root of we randomly select the square root of the number of predictors and we fit the random forest model. Gradient boosting machine method test error was significantly higher. In the following code, we demonstrate the boosting that boosting can overfit. We use the tenfold cross-validation method since the sample data set is small. Let's look at the first few lines of biodeg data set. Let's look at the number of rows of dataset and let it be equal to n. Let n equal to n row of biodeg, so n equal to 1055. Let's find 10% of the number of rows of dataset. Let n1 equal to round bracket 0.1 times n. 0.1 times n is 105.5 and we round it to 0 decimal place and that comes to 106. So n1 equal 106. Shuffle the data. Let biodeg equal to biodeg and square bracket sample bracket n comma n and then place the comma and leave the other space because we are going to select all the data rows. So size of the cross validation, let k equal to 10. Function to find the index for the test set. Let test.set equal to function of input I, n, k. We know n equal 1055. We know k equal 10. And this I will be the new input. Curly braces. If I less than 1 or this double vertical line means or I greater than k, then stop and print the message I out of range of bracket 1 comma k. Else start equal 1 plus bracket I minus 1 times n1. End equal if I equal k, comma, then n. N is 1055. Else I times n minus I times n1, and n1 is 106. And then start colon end. So start to end. Close the bracket. Show working. So test set 2 comma n comma k. So in this case we calling the function test.set, and the inputs are 2 comma n, which is 1055, and k, which is equal to 10. So if I less than 1 or I greater than k, but I is equal to 2, so start equal 1 plus 2 minus 1 times n1, so that's 107. So start is 107 and end is if I equal k, but I does not equal to k, I equal to 2, then I times n1. So 2 times n1, 2 times 106 is 212. So start 107, end 212. And then the rest of the numbers are printed inside that range. So these are the indexes of the test set. Initiate train error vector. Let a dot train equal s dot numeric open and close bracket. Initiate test set vector. Let a dot test equal s dot numeric open and close bracket. Show working. Let index equal test dot set of 2 comma n comma k. So that prints start is 107, end is 212, and all the rest of the numbers are printed in between. Show working. Let test equal biodeg square bracket index comma and then the rest of the rows. So index it will print for biodeg index number 107, 108, 109, and so on up to biodeg index number 212. And so this is how it looks like. So show working. Let train equal biodeg of index minus index comma all the row values. So minus index means those index numbers that were selected for the test data set, those index values are not selected here. So let's look at the first few lines of the head data, and that looks like this. Show working. So let train 2 equal Columbine of train comma class 2 equal has dot integer of train at class minus 1. Ahead of train 2 that prints the first few lines. So we see that the train data is binded with the class 2 column. And class 2 column is the integer value of the class column minus 1. Then we set dot seed of 1, 2, 3, 4, 5 because this gradient boosting method function gives us the random values. So we don't want the random values, we want to stick to one value. So let R equal GBM of class 2 equal all the predictors except class, because class is the response variable, comma data equal train 2, comma distribution equal Bernoulli, comma n dot trees equal 3000, comma interaction dot depth equal 5. So that gives a gradient boosting model. A gradient boosted model with Bernoulli loss function. 3000 iterations were performed. There were 41 predictors, of which 39 had non-zero influence. Working, let pred.train equal predict of r comma new data equal train comma type equal response. Using 3000 trees, head of pred.train equal these values. These are the predicted values. Let y head underscore train equal pred.train. If it is greater than 0.5, then plus 1. Else it is, and if it is not greater than 0.5, then if it is greater than 0.5, then this will return 1, then you plus 1. Otherwise, this will return 0, and when you add 1, that comes to 1. So the value is 1 or 2. Working and row of train, that gives the number of rows in the train dataset, and that's 949. Let a dot train equal mean of s dot integer of train at class not equal to y head underscore train, and that is 0. Let pred.test equal predict of r comma new data equal test comma test equal type equal response, and using 3000 trees, so the pred.test values are these. Working, so let y head underscore test equal pred.test. If it is greater than 0.5, then this will return 1, and then plus 1, this returns 2. Or if it is not greater than 0.5, then pred.test greater than 0.5 will return 0, and add 1, that will return 1. Working, let a dot test equal mean of s dot integer of tested class not equal to y head underscore test, and that is 0.1698113. Apply cross validation on boosting method. For I in 1 colon k, so 1 to k, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we are forming a loop. So we will perform those functions, those commands that we showed previously for the k equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So open loop, let index equal test dot set of I comma n dot comma k. Then let test equal biodeg of bracket index comma all the rows values, and let train equal biodeg of bracket minus index comma the row values. Requires integer values for classes. Let train2 equal columbine of train comma class2 equal s dot integer of train at class minus 1. So now we need to pass the command set.seed of 1, 2, 3, 4, 5, because we are calling the function gbm, and that gives the random values. So fit the boosting model interaction depth between 1 and 5 is sufficient. Let R equal GBM of class 2 equal to addition of all the predictors except the class. Data equal train 2, distribution equal Bernoulli, n dot trees equal 3000, interaction dot depth equal 5. Predict train test. Let pred.train equal predict r comma new data equal train comma type equal response. Compute the predicted class levels. Let y head underscore train equal pred.train greater than 0.5 plus 1. So pred.train, if it is greater than 0.5, it will return 1, and then when you add 1, that will return 2. And if it is if pred.train value is not greater than 0.5, then it returns 0, and when you add 1, that returns 1. Classification accuracy, resubstitution. Let a.train I, so the position, the location is I. So how many values will go in a.train? 10, because I is running from 1 to k, and k equal 10. So a.train bracket I equal mean of s dot integer of train at class not equal to y hat underscore train. Predict test set. Pred.test, let it equal to predict r, comma, new data equal test, comma, type equal response. Compute the predicted class levels. Let y hat underscore test equal pred.test greater than 0.5 plus 1. So if pred.test value is greater than 0.5, then this returns 2, otherwise it returns 1. Classification accuracy substitution. Let a.test I, position I, equal to mean of s dot integer of test class not equal to y hat underscore test. Close the curly braces, and so this it will run 10 times. Let's count these messages, and it should be 10. So 3, 6, 9, 10. 3, it's more than. So how many times this will run? This will run, so for I equal 1, for I equal 2, I equal 3, 4, 5, 6, 7, 8, 9, 10. And interaction depth is so it should run 10 times. And the GBM function runs 3, 6, 9, 10, 13, 14, 15, 16, 17 times. Print train error and x 0, and these are for the 10 values of I. Print test error a.test and x 10 values of the misclassification rate, which is printed here. Number of rows of data set, let n equal n row of biodag, that's 1055. Okay, so what we are doing over here is we are repeating the same function, finding the 10% which is of the number of rows, which is 106, and then shuffling the data, and then size of the cross validation k equal 10, and we are repeating those functions over here, and these are the a dot the test errors. So the train errors are all 0 and the test errors are non-zeros. In the following code, we will plot the train error and test error to show that boosting method is overfitting the data. From the plot, there is a, okay, let's have a look at the plot. Okay, so what we did, plot of train error and test error. So plot of a dot train, so this will plot the train data first, comma, y limit equal continuous, bracket 0, comma, maximum of a dot test. So maximum of a dot test, which looks like is 0.17924528. So this y-axis runs from 0 to the maximum of a dot test value, and y label equal error rate. So y label is error rate, and type equal L. So it will be a line, color equal blue, and then we plot lines for a dot test, and the color equal red. Then we want the legend, bracket top right, comma, legend leg equal continuous train, comma, test. So this is labeling the legend, comma, color equal continuous blue and comma red, comma, LTY equal 1. So LTY uh, is the strength of the line, comma, CX equal 1. So this is the size of the legend box. Comment, from the plot we visualize that there is a big gap in between the test error rate and the train error rate at each point. For this reason, the gradient boosting method, machine method, is overfitting the data. Okay, summary. Lastly, we completed the task by demonstrated that boosting can overfit by using tenfold cross-validation to find the test errors and plotted them along with the training errors. From the plot, we visualized that there is a big gap in between the misclassification error rates of the trained data set and the test data set. This indicated that gradient boosting method is overfitting.